Hello, you all. This is Darrell Lee Berry Jr. I'll be finishing my progress through the chapters and sections I'll be having an exam on this Thursday, tomorrow, and in the algebra. I'll be going through sections 2.1, 2.2, 3.2, and 1.5. This is part 4. We're in the middle of section 2.2 right now. So see the previous video for 2.1 and some of 2.2, or the previous 3 videos from 2.1 through the middle of 2.2. So I'll see if I can get through 2.2 and 3.2 in the next hour or two. And then I'll redo 1.5. I started 1.5, but there was a few pages left. But I'll do the full 1.5 again, and hopefully I can get to some homework problems tonight. So all day, some linear algebra. So subscribe, like. I'll show the links again by the end, and we'll go ahead and get started. And what I may do is actually even increase this some. Go. So I'll share the links again. But for now, we'll get the data rolling. And I shall move this over to the side a bit. Keep in mind that I have tutoring available, individual or group. Just let me know if you're interested. We can get something started. You can pay it through PayPal or Patreon. So you can sign up for that. And let's go ahead and get started. So one example 2. So this is 2.2. Example 2. So it says, expanding on the previous example, we consider the linear transformation. So the linear transformation is mu a. You're transforming something from R2 to still in R2 for some specific A, the 2 by 2 matrix, and give geometric interpretations of these maps. So I know this is important. So we have if. So if you saw my video previously, this will be our hypothesis for our proof. If A equals 0, 0, 0, 0, which is the 0 matrix, then AX equals 0 for all X vectors in R2. Remember, we talked about how we have to make sure we put our conditions in the proof in the last video. So if that is the 0 vector, the 0 matrix, then that equals 0 for all X. Therefore, this transformation, mu A, sends all vectors in R2 to the 0 vector. And it also says if the B matrix is 1, 0, 0, 1, so that's the identity matrix in the second dimension, then Bx equals X. for all vectors x that are in the second dimension. Therefore, the function mu b is the identity map from R2 to R2. That's A. All right. So now I was asking to consider a transformation. So now we're on the consider part. Consider the linear transformation. So this is B. Consider the linear transformation T is a transformation, R2 to R2. Defined by the matrix A equals 1, 1, 0, 1. The effect of T is pictured in 2.1. One might slide a deck of cards in this fashion, and such a motion is called a shear. So let's look at this. All right, so this is a shear. So B is the identity matrix. A is the zero vector. Well, in part A is a zero vector with all zeros. B is the identity matrix. One's down the diagonal because the first column here will duplicate the first column, and then the second column here will duplicate the second column, and that'll end up being another 2 by 2 matrix with the same first and second column. So that makes sense. So this is a shear, meaning it's sort of like if you take a deck of cards and slide it, okay? Let me draw this out. Yeah. So C, we have let A equals 0, -1, 1, 0. Then we have A, x1, x2 equals 0, -1, 1, 0. Times x1, x2. So then that will be x1, 0, 1 plus x2, -1, 0. And our matrix here is a 2 by 2 and a 2 by 1. So what we end up with has to be a 2 by 1. So we know we're going to add those. So that's going to be negative x2 and x1. So that must be the 90-degree one. And we see in figure 2.2 that AX is obtained by rotating X an angle of pi over 2 counterclockwise. So this is the 90-degree counterclockwise rotation. D, let B equal 0, 1, 1, 0. Now this is the reverse diagonal of the identity matrix. Then Bx equals 0, 1, 1, 0, x1, x2 equals x1, 0, 1 plus x2, 1, 0. So that equals x2, x1, as shown in figure 2.3. So this is 2.3. So this is a line, and this is y equals x. This is x, and this is bx. So basically, it rotates it around the line at 45 degrees. We see that bx is the mirror image of the vector x reflecting across the mirror x1 equals x2. In general, we say the transformation R2 to R2 is given by reflection across a line L. If for every x in R2, the transformation of x has the same length as x, and the two vectors make the same angle with L. So the same length, same angle. E. Continuing with the matrices A and B from part C and D respectively, let's consider the function mu AB, which is R2 to R2. And we know that mu AB equals mu AB, which equals mu A mu B x. It's a linear transformation that gives the reflection across the vertical axis because it turns 90 degrees and then it reflects. Because A is the 90-degree rotation. So it turns 90 degrees first, and then mirrors across that line. So AB equals 0, negative 1, 1, 0, 90 degrees, and then 1, 0, 0, 1, mirror. So that equals, it's going to be a 2 by 2. This is going to be 1 0, 1, plus 0, 0, 1, and 0, 0, 1. 1, 0, 0, 0, 1, minus 1, 1, 0. So that equals 0, 2. No, correct. Right side is multiplied by 0, 0, 1, and negative 1, 0. Hold up. What did I mix up? Oh, my mistake. I rewrote the same matrix twice. Well, I'm getting something different. So let's see what I'm doing here. I wonder why there is a swap. So I must be doing something incorrectly with my matrix multiplication, but I don't see exactly what. So basically, we can say that so this one and this 0, and putting here, multiplying by each of the columns, and then this 0 and 1 and 1, and putting here. I'm extracting the negative from that column and putting it on the outside. We have 0, 1, and negative 1, 0. So let's see what I swapped around. So basically we have A1, 1, A1, 2, A2, 1, A2, 2, and B1, 1, B1, 2, B2, 1, B2, 2. And we know we have to match them all so that the insides match. So we will have A11, B11 plus A12, B21, then A21, B11 plus A22, B21. That seems to work. And then we have A11, B12 plus A11, 1, 2, B, 2, 2, and A, 2, 1, B, 1, 2, plus A, 2, 2, B, 2, 2. And so this is what we have. Now, I believe I have that there. For matrix operations, that's the scalar. All right, so this is what I was writing here. Oh, hold up, that was a plus. Looking at this example here, I do have 4 minus 3 is 1. Just like here, I have 0. I want to work this a different way. So I have 0, 1, plus negative 1, 0, 0, 0, plus negative 1, 1, 1, 1, plus 0, 0, 1, 0, plus 0, 1. So that equals 0, 1, and negative 1, 0. Still get the same thing. Give me a moment here. I'll check on the calculator site. Right, so I have here